Welcome to section 9.6 functions. Please make sure that you've watched the introduction to functions video before watching this one. Pause the video often, completing the problems with me and on your own. Here are the topics and objectives, the standards, vocabulary, and concepts. So when we talk about function, as you saw in the previous video, it's a rule that assigns one output to each allowable input. We often call the input we call the inputs domain and the outputs range, again, as you saw in the previous video. Often you'll see functions portrayed as machines. So inputs go in, the machine does something to them, and then the output is the result. So here you see a doubling function. So whatever comes in comes out double. We can also use functions to describe how two quantities are related. So a function tells us how an input determines an output, or how the output depends on the input. So to describe a function in words, we say that the allowable inputs are, and we give the rule, and then that will be the outputs associated with that. So even if our goal is to describe a function with an equation, we can clarify our thinking about the inputs and outputs by first describing it in words. So let's look here at this blue whale function. So we're talking about this blue whale function. And it basically assigns a year since 1950 for the number of blue whales alive at the end of the year. So there's unlikely that there's a single formula that describes this function exactly, but biologists might seek a formula to closely approximate the function and help them make predictions. So that's mathematical modeling. So we can model the blue whale population with the function by describing it in words. So let's look here. So let's explain why the next proposed function is not a function. And again, the rules of what makes a function are in the previous video. Modify the allowable inputs and or the rule to describe a function that is relevant. All right, so this is the context. Purchasing a paint at a paint store. So the allowable inputs would be the numbers between 0 and 1,000. And the rule is to any input D, associate the number of cans of paint C you will get if you spend D dollars at the paint store. So let's think about this for a second. You're spending D dollars and you're getting C cans of paint. So right now it's any number that goes in for 0 to 1,000, and then that's whatever. So let's say you spend $10. Well, maybe you get 1 gallon of paint. Maybe you spend $10 and you get half a gallon and a quarter of a gallon. Maybe you spend $10 and you get 2 half gallons. So do you see here how one input, so if we were to do a mapping diagram, it would kill the frogs, as we say in the other video. We're going to way too many different outputs here. You remember, you can only go to 1. So that's why this is not a function. But we could modify this by saying, okay, for D dollars, that's the input. The output is going to be the number of, let's say, brand A, whatever that is, gallon cans of paint. So now we're being really specific. We're saying the brand and the gallon because that will only have one output for the amount of money. And here it is written out if you want to pause it and read through it a little more carefully. So go ahead and you give this a try. Press play when you're ready to see the solution. And there you go. So we can also represent functions with tables and graphs. The graph of a function is all the points in the coordinate plane where the first coordinate is an allowable input and the second coordinate is the output of that first coordinate. So suppose, and we're going to do this example in a moment, that we're going to be looking at plant height function, where the inputs are the number of days and the outputs is the height. So let's take a peek here. So here is our graph of the plant height function. So when did the plant sprout? When did it begin to grow? So you might want to look at the table. I'm going to look at the graph actually, and I'm going to say, okay, when did it start to grow? Well, at 0, there's going to be no height. So it started to grow after day 4, and you can see it in the table, right? That's where it starts to grow, and you can see it right here in the graph. So after day 4. When is the graph the steepest, and what does that tell you about the situation? So when we're trying to find the steepest, we can look for the difference between 2 days. So the difference between these 2 days is 0.5. The difference is 1, so that's already steeper. The difference here is 1.5, that's steeper. The difference here is 2. The difference here is 0.5, 0.5. So the difference that's the greatest is between day 7 and 8. And on the graph, what this would look like is this portion here what is the steepest line? And it is really hard to tell what's steepest. The table really does help us out. So that would be between day 7 and 8. When did the plant meet its maximum height? So height is our Y here. So when did it reach its maximum height? Well, where is the highest? So on the graph, we can see that it's highest here. And so when did that start? At day 10, and maybe you can look at on the table. And how tall was it? Again, you can look at it here, or you can look at it on the y-axis. So if we notice that the graph is a curve that connects the point, why are we allowed to connect the point? Sometimes we don't connect points. We can connect the point because in between the times that the plant was measured, the plant has a height. So that is the space in between. So between day 4 and 5, that plant is still growing. We're just not measuring it. Let's do another example together. So a patient receives a drug. This situation gives rise to a drug function for which the input is the time elapsed, so the time in minutes, since the drug was administered, and the output is the amount of drug in the patient's body. The graph of the drug function is shown. Give the approximate coordinates of point A and discuss the significance of this point in terms of the scenario. So here's A. Remember that coordinate points go X, Y. So that would be, looks like it's about 7. And the height, maybe we would say 55. It's the approximate coordinates. So what does it mean? Well, just this itself, 7 minutes, and then this is the amount of drug in the system. So we could say that this is, after 7 minutes, there's 55 milligrams of the drug in the system. But what about the scenario? Well, that's the highest point. That's the maximum amount. So this is the maximum amount of drug in the bloodstream, and the time that it released, and the time that it happened. The max amount of drug and at what time. So give the approximate coordinates of point B. So point B looks about maybe 22, that down, and then maybe 5 again. And again, so that's at 22 minutes, the amount of drug was 5 milligrams in the bloodstream. But it also is the lowest part of the graph. So this is the minimum amount of drug in the bloodstream, and at what time. Overall, discuss what the graph tells you about the patient and the drug. So if we look at this graph, we would say, okay, really quickly, we got to the maximum, right? And then pretty much just as quickly, it started to decrease. And then it went up a little bit more, but it pretty much leveled out around 15 milligrams. So that is how we would describe this graph. And if you want to see all that written out, here you go. And then you go ahead and give this a try. Press play when you're ready to see the solutions. There we go. All right, let's take a look at another example. I believe actually that this is example 4. Sketch 3 different graphs that could fit with these 3 hypothetical descriptions of how the federal debt might change over a 5-year period. For each graph, explain why its shape fits with the description. Your graph need not show specific values for the debt, but be sure to indicate what each axis represents. All right, so here, what they mean when we talk about like each axis, we don't need to say like 1, 2, 3, 4, but we do need to say what is the X and what is the Y. So we're talking about debt and time. So our time is always going to be our X, our independent, and then the debt depends on the time. So looking here, we've got debt and time. So for the first one, the debt shrinks, but it will shrink at a decreasing rate. So maybe it starts up here and it decreases, but it's shrinking at a decreasing rate. So it's shrinking less and less over time. So maybe it shrunk a lot, and then a little, and then a little less, and a little less, and maybe it looks like that. All right, B, we've got time and debt. The debt shrinks at a steady rate. So, okay, it's going down, and then down, and then down, and then down. It looks like a line. That's a steady rate. All right, let's try letter C. The debt shrinks, and it will shrink at an increasing rate. So it will start, and it's going to go like this. increasing rate. It's shrinking at an increasing rate. So it might look like that. Might have like a little hump on it there. So let's make sense of that a little bit more. Here are the graphs as well, if you want to read that over. And then you go ahead and give it a try. I've given you the X and Y axis here, and then press play when you're ready to see the solution. And then we'll pick up in the next part.